problem types. Let's look at a smaller example of this. This is manifestly a natural number. 21 over 7 certainly reduces to 3, so we can say it's a member of the natural numbers. Okay, even though it has a fractional form, it does reduce to 3. Now, this problem we're about to work on today is much larger than this. 69 factorial has what? How many digits? I don't know, over 100 digits. So we want to know that 69 factorial plus 12 divided by 73 is a natural number, just like this was manifestly a natural number. Now, what I'm going to do here is work it more in terms of modular arithmetic, and I want to write down an equivalent statement, which I will prove for you. 69 factorial, again, a number so big you can't even say it. This statement right here is the same thing as saying 69 factorial would be congruent to negative 12 mod 73. Okay. Now what this says is that you take the difference of these two numbers and it will be a multiple of 73. Okay, we will show that. Okay. Now, we're going to start with something that's quite familiar to you. This is just a special case of what we call Wilson's theorem, and this left-hand side's in the form p minus 1 where p is a prime, p minus 1 parenthetically factorial, okay, is always congruent to negative 1 mod p. And this holds for all prime numbers. And the basic reason it holds, it's an elementary proof that appears in any number theory book I've ever seen. But it's the fact that any natural number less than p is going to be relatively prime to p, and that means it's going to have a multiplicative inverses. And those multiplicative inverses have products of 1, is why this works out. And p minus 1 is the only one that's left over. Okay? So that's essentially the proof of Wilson's theorem, although it's a little more formal than that. But that's the basic, view from 30,000 feet. So this very first statement is just using this result called Wilson's theorem for p equals 73. In other words, this is p for p is equal to 73. And again, the result only holds for prime numbers. You can prove pretty quickly that it doesn't work for composite numbers. All right. Now, so this piece right here is just a rewrite of 72 factorial. 72 factorial is the same as 72 times 71 factorial. But notice that 72 itself is congruent to negative 1. And I'm not going to do all this. I'll just do a few of these. 72 itself is congruent to negative 1. Okay? Because when you subtract that, you get 73, right? And so that's how this statement right here became this statement. You could replace this with negative 1, multiply through, and you get 71 factorial is congruent to 1. Okay? So that's just an example of the power of the modular arithmetic. Now, in a similar fashion, we rewrite 71 factorial as 71 times 70 factorial. Okay? And once again, right here, you can see that 71 is congruent to negative 2. So you see, congruence is the modular arithmetic notion of equality. It means about almost the same thing as equality in some sense. So we replace this with what it's equal to. What's that? 71 minus negative 2. Sorry, that's 71 minus negative 2. Okay, and so we replace 71 with negative 2 right here, and you can see right here this is pretty easy in terms of just what you would expect. All right, and we just keep on going here, folks. I'll try to leave out some of the commentary. And you can check out the steps yourself to make sure I haven't made a mistake. Now, what we can do right here at this point in the problem, though, is note that minus 1 is congruent to 72 again here. Right? Minus 1 is congruent to 72. And so when you divide through by negative 6 right here, you're going to get 69 factorial. Okay, 69 factorial. Now, if you divide 72 by negative 6, you get negative 12. Okay. And so y'all, again, I'll write down mod 73 for the sake of, I left it out. It's understood we're doing mod 73, but as our final QED statement, we'll call this mod 73 just to be clear on what was going on the whole way through that. Okay, and that means the same thing as saying that 69 factorial plus 12 is a multiple of 73. Okay, so this is our QED statement right here. And so basically, we started with Wilson's theorem and worked our way all the way down from 72 factorial to 69 factorial. Okay, and that does it. And y'all, there's a generalization of this that appears in Underwood Dudley's number theory book. He actually generalizes this, and it's something that's I haven't seen in a lot of number theory books. A lot of people think of Wilson's theorem as kind of a one-stop thing, but you can modify it to various intermediate results that'll help you prove other things. Okay, so anyway, that does it, folks. Should I write QED here? Quandam est demonstrandum. Okay, that's all.